6.3, and this is and stuff. So we're going to be doing and probabilities. So most of the probabilities we're going to be doing is multiplication. Okay, so we're going to talk about independent and dependent. We're going to talk about conditional. We're going to talk about, sorry, this moved on me. I'm not sure what's up with this pen today. Defining the conditional probabilities. So we're going to talk about independent events, dependent events, given probabilities. This is all review from regular stats, except probably maybe tree diagrams. I'm not sure if you did tree diagrams in regular stat. Okay, here we go. So if two things are independent, and remember this intersection really means and. So if you look at it this way and put a little thing, it's an A, and it's an and probability. That means to do the first one and then do the second one. If two things are independent, each of these things have no bearing on each other. Things that are independent to people having the same birthday, unless you're talking about, like twins or something like that, the probability of two people having the same birthday is independent. Here's an example, a real life example. It says, following the Space Shuttle Challenger, it was determined that the failure of O-ring joints in the booster rockets was to blame. So, under cold conditions, it was estimated that the probability that one of the O-rings would function properly is 97%. So, NASA, who's famous for making simple mathematics mistakes and costing billions, and a lot of people died in this Challenger disaster, thought, okay, well, if it's cold, the probability of this O-ring still working is 98%. So that's pretty good, actually. All right. But the problem is that there were 6 of these O-rings, and each O-ring was independent, so it didn't matter. But you had to get all 6 to work properly. So the first one, the second one, the third one, the fourth one, the fifth one, and the sixth one all had to function properly at 97.7%. Okay, so if you look at it as one, it's a 98% chance that you're going to be okay, 2% failure rate. But if you look at all 6 of them, because if one of them goes bad, it blows up. If you look at all 6 of them having to function properly, that's 0.977 to the 6th power, 0.9776 times. When you calculate that, that comes out to approximately 87%. So instead of NASA thinking that, okay, it's cold out, but it's still a 98% chance it will be okay, it really wasn't, because there's 6 of them. It really was an 87% chance of the O-rings being okay. So what's true about independent? If these things have no bearing on each other, then you're just going to multiply them together. Okay, that's independent. This doesn't affect this. This doesn't affect this. Okay, now, if the two things are not independent, these are dependent events. Okay, dependent events do have an effect on each other. Still an and, still put a little A there, still an and, still an intersection of the two things. And you're going to do probability of A because it comes first. So that's your independent probability. The second probability depends on what happens here. Okay, and I'll show you with cards in a second. So this reads, find that probability of A given, remember this slash from regular probability means given you've already done, let's supposed to say given. Oh, there it goes again. Given the fact that you've already done A. So find this probability of B given that I've already found the probability of A. A simple example is pulling cards from a deck. So let's say we do the probability of 2 spades from a deck of cards. If we're going to do it as an independent, the first time you pull a spade is 13 out of 52. If you replace the card back in and shuffle, the next time you still have 52 cards and there's still 13 spades. So that's independent. An example of dependent is the same problem, but all I'm going to do is change up and say don't replace. So deck of cards, first probability in the deck of cards, 13 out of 52 times second one. Now, I don't replace. This second probability, which is called a conditional probability, depends on what I pulled out here. First of all, I had 52 cards. Now I only have 51. Now, whatever happened here will depend on what happens here. If I pulled a spade out and then didn't replace it, I only have 12 spades left. That is dependent probability. This second thing right here is called conditional probability because this probability is based on the condition that this happens first. So in intersections, in ands, you're going to multiply. You have to think it through. You're going to do the first one, and then you're going to do the second one. It's independent if these two don't have any bearing on each other, then it looks just like this. But if this one is dependent on what happens here, then it's going to look like this. Okay. This tells me that do this B probability given the fact that I've already done A. All right, so let's look at a two-way table with this. All right, so consider the two-way table. E is that it comes from an English and physical science course. That's this. This is the SP. EPS, I'm sorry, EPS. And this is that the grade is lower than a B. Okay, so this is your L. This is the lower than a B. All right, it says find the probability of lower. All right, so we total 10,000. And then we want to find the probability of lower. So it's just 3, 6, 5, 6. Simple probability. Okay, now this says find the probability that it comes from English, and E stands for this English and physical sciences, given that the grade was lower than the B. So basically what this is saying is out of all the people that got lower than a B, how many of them were in English and physical sciences? I say that again. So given all of the fact that all the people that were lower than a B, how many of them were in English and physical sciences? All right, so here's the trick. If you have a table, it's super easy. This slash is literal. It means given. That's all I'm given. The rest of this chart is going to disappear. This is all that I'm given that L. That's all I'm given. That is all I'm given, then the problem becomes easy. How many English and physical sciences, engineering and physical sciences, 800 over 356. Oh goodness, 800, I'll clean that up, over 3656. And I know it looks like I'm an idiot, but the problem is that this pen is acting up and I'm left-handed and it's an electronic pad. And if I don't keep my hand up, it like drags on the electronic pad. I've tried 3 different pads. It's just my left-handedness. Anyway, okay, so let me go over this. That given tells me that's all I'm given. This becomes your denominator. So the L becomes your denominator. I cover everything else up, because that's all I'm given. And then I just do the numerator, engineering and physical sciences. Okay, now let's try a different one. Let me clean this up. Start over again on my chart so I can see my numbers. All right. It says, now find B given E. Okay, so I'm only given the E now. So this is all I'm given. Everything else is going to be covered up. Don't need this, don't need this. Look at what you're given. So you're given this E. Everything else is going to be covered up. And this becomes your problem. Okay, so then the denominator is E, which is 1600. And the numerator is L, which is lower than a B, 800 over 1600. And I'm not simplifying any of these. One, you don't have to on the AP exam, like I said before. And two, I want you to see where these numbers are coming from. All right, so if it's a given in a table, it's a given in a table, then you're good to go. You just cover up everything else except what you're given. The slash means given only this, given only this. All right, now let's talk about how to test to see if things are independent or not. Okay, so if two things are independent, then A and B have nothing to do with each other. So that means if I do A given B, this B wouldn't have any effect on it, and the probability would just be the answer to A. Okay, so if let's do it with the B. If I say given A, if I'm only giving you A, if it is dependent, this and this will have two different answers. If they're not, then that means this A has no effect on B and it's just B. So this is a test for independence. And on your notes, when you're copying these down, this is going to be what I call a 5-star. This is on the AP exam every single year, and therefore it's going to be on my tests. And they always ask you if two things are independent. So here's your test. Pick one of the two things. It doesn't matter which one you pick. Let's say we pick A. Find that probability. Then find that probability again given the B or given the other one. If these two come out to be a decimal equal, they're independent. So if they're equal, they're independent. If they're not equal, then they're dependent. Okay, so here's an example. Are the events male and left-handed independent? So I picked one of them. I'll do it both ways. It doesn't matter which one you do. I'll do it the other way in a minute. Okay, so I'm going to do left-handed. The probability of being left-handed is 7 out of 50. Okay, now I'm going to do left-handed again, given the other thing, the male. So given males, I'm only looking at males now. So I'm only looking at males because that's what I'm given. I'm only looking at the males. There's 3 out of 23 left-handed. Okay, then you test it. Is 3, out of 23, my hand gets crampy because I have to hold it a weird way, is equal to 7 out of 50. Is 3 out of 23 3 out of 23, that's your left-handed, given male, equal to just left-handed. And just left-handed was total 7 out of 50. Those are not equal as a decimal. If you divide them, they're not equal. Therefore, they are dependent. Okay, so let's do the other one. Let me put this. So, okay, let's do it the other way. It doesn't matter which one you choose. So I'm going to pick male. So I'm going to find the probability of male and see if that is equal to the probability of male again given left-handed. So pick one, pick it again, given the other one to see if the two are equal to each other. Okay, so males. I have 23 out of 50 males. Okay, so 23 out of 50 males. Equals. Then I'm going to do males given left-handed. So everything else is going to disappear. Given left. Given left. So given left, how many males do I have? 3 out of 7. Are these two equal? No. Therefore, they're dependent. So pick one, pick it again, given the other one. So I did males, total males, 23 out of 50. Then pick it again, given the other one. Now I'm only giving you left-handed. 3 out of 7 males. Not equal, they're dependent. I'm on the edge, so I keep doing that. Okay, so definitely on the test. And this is something new, I know it is. Okay, let's talk about tree diagrams. So we're going to talk about tree diagrams. We're going to flip a coin twice, and we talked about this the other day. So how do I do a tree diagram? This is flipping a coin once, and then I'm going to flip it again. That is a tree diagram. Each probability here is a half, a half, a half, a half, and a half. That's a 2. Sorry about that. Okay, so here are the rules with tree diagrams. If you're going through a branch, as you're going through branches, like heads and heads, did you hear the and? Or heads and tails. So as you're going through the branches, you're going to multiply your numbers. If you're in between, do you see this? How this is kind of like an in between? It's from your first branch, it's either this or this. When you first flip a coin, it's either heads or tails. So you're going to add in between the branches. Multiply through, add in between. That's your rule for probability, for tree diagrams. So multiply through, add in between. All right, so let's take a look at one. It says, what percent of adult internet users visit YouTube? Okay, so in tree diagrams, it doesn't really matter when you're setting it up if it is dependent or not, but this is dependent. If you go on YouTube, you had to have gone on the internet first. So if this is your A, B cannot happen unless you did A. That's why this is a dependent probability. Okay, so this would look like this. You would have this probability, and then I'm not going to set up the whole thing to save you time, but you would have, sorry, I'm not sure. Are we still sharing? I think I'm still sharing. I'll edit that out. Anyway, something happened there, didn't it? Okay, so we are doing internet use. So we have 99 watch between 18 to 29, use the internet, and 1% don't. I don't know who the 1% is that don't. And then you have YouTube. So this 1% don't use the internet, but 99 do, and of those, only 40% to 60% are not right, are they? So 40% do use YouTube, and then 60% wouldn't. 99 use the internet, and remember that complement symbol, that would be IC. This would be YouTube C. Each one of these is going to be the same, 30 to 49. Okay, this would be 96 and 4%. And then it would be, if you're on the internet, you're going to use YouTube, 30%, 70%. These numbers are not right, are they? We're going to do a whole bunch of these in class together. Okay, so you would do that 4 times over. I'm not going to take the time now so you don't have to do it. Okay, but so here's what you would do. You're going to go through and you would multiply this branch. You're going to go through, multiply this branch, because the question is internet and YouTube, internet and YouTube, internet and YouTube. So you're going to multiply, 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 multiply. So this and this, this and this, this and this, this and this. Then these are not ands, these are ors. So you're either this or this or this or this. So these are actual pluses in between. So to do this problem, your answer is going to be 99 times 0.4 plus 96. Oh, this is frustrating. I'm going to have to try and change try a different pad. 30 plus 87 times 16 plus 64 times 14. Okay, and then you would add all those up. Multiply, 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 multiply. So this times this, this times this, this times this, this times this. Why multiplication? I'm on the internet and using YouTube. Internet and using YouTube. YouTube. And then you're either this age or this age or this age or this age. And then you would multiply, 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 and then add them up. We're going to do a whole bunch of these in class together. Okay, last one. Here we go. What is the probability that a randomly selected resident who reads the USA Today also reads the New York Times? All right, so reads the USA Today, reads both, reads the New York Times. Here's your and right here. Do you see that and? That's your and. So that's 5% right there. All right, so watch this one. This is easy on a Venn diagram. So on a Venn diagram, you have those that read either this paper or both, and then these wouldn't read, this 40% doesn't read either. All right, so the question is, what is the probability that a resident who reads the USA Today also reads the New York Times? Okay, so who reads the USA Today? So given, see this, given they read USA Today, so that's your given, that becomes your denominator. Who reads, given that they read the USA Today, also reads the New York Times? Okay, so watch how easy it is on a Venn diagram. You are given USA Today. This is USA Today. So that's all you're given. See this circle? That's what you're given. Cross out everything else except what you're given. Just like on a table. Cross everything else out except what you're given. So you are only given 40%. Because 40% of the population reads USA Today. So just like on a table, when you're doing a given, you only do what you're given. Then out of that, out of what you're still left with, what percent read the New York Times? Well, 5%. If you put your pen down, those are the people that read the New York Times right there. It's ugly. Oh my goodness, my phone is just going crazy. And then you just divide them. Okay? All right, we'll work on more of this in class. Here's a review of that section.